So yes, this is where we were up to. Talked about two the important no-go theorems for quantum theory, or Untitled theorem, and various different notions of contextuality. Today I'm going to present a much more recent theorem, which, well, as it says there, has to do with Scientology, but we'll come to that. Now, when previously with Bell and Cauchy and Specker, I pretty much just jumped straight in there and presented the theorems themselves pretty quickly, because I figured they were well known and I sort of wanted to get to saying some newer stuff. This one, however, is much more recent, so actually I'm just going to be spending most of the lecture presenting slowly and carefully this one no-go theorem. And also spending much more time sort of setting it up and motivating the question that we're asking. So this is a quote from Ed James that well, people seem to like, because actually I keep seeing this in talks over and over again, but I like it too, so it's in my lecture. So here's what he says. Our present QM formalism is not purely epistemological. It's a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelette that nobody has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in basic physical theory. We cannot separate the subjective and objective aspects of the formalism. We cannot know what we were talking about. It's just that simple. So let me begin with a case where we certainly can separate the subjective and objective aspects of the formalism, a case that we understand well, just so that we can see what we mean by that. So let's talk about classical mechanics just for a minute. Consider a single classical particle. Let's say it's moving in one dimension. So the particle has position and it has momentum. And the state of that particle is completely determined, completely described by the two values, the values of x and p. And other physical properties that this particle might have are functions of x and p, for example, energy. Okay? And, well, we can think of its state as a point in phase space being two-dimensional, parameterized by x and p. And the motion of the particle will be determined by Hamilton's equations, which, as it happens, look like that. Okay, so that's fine. Now, sometimes we don't know the exact microstate of a classical system. The information that we do have defines some probability distribution rho over the different physical states. So that's a distribution rho over this phase space. Now, of course, rho is not some kind of physical property of the particle. It reflects my information about the particle. Or if you want to use a slightly different terminology, you might say, some physicists prefer to say it describes an ensemble of particles. But it's certainly not a physical property of an individual classical particle. The particle itself occupies a definite point in phase space at all times, and does not care what probabilities I might have assigned to different states. But still, the probability distribution does obey a definite law. You can figure out how it's going to evolve because you know how the underlying microstates evolve. And the evolution of the probability distribution is given by the Valville equation like that. Okay, so just a little terminology. In this case, the word state is used for too many different things. So the word terminology, the terminology here is just to separate things a bit. The real state of this thing, that's the thing that's characterized by x and p, we could call the ontic state. That's what's actually there. And the distribution rho we could call the epistemic state. Epistemic because it affects my information. Okay, and there we see the objective and the subjective aspects of the formalism, as James was saying, nicely separated out. So, a sort of question or debate that goes right back to the early days of quantum theory asks, what is the quantum state? One point of view says that it's ontic. This is more like the x and p of the classical particle. So a quantum wave function on this view, you might say, is a real physical wave of some kind. And indeed, quantum interference does seem most easily understood this way. What's going on in a two-slit experiment if it's not the interference of some kind of wave? Although, just a point of caution already, this wave is defined on configuration space rather than in normal three-dimensional space. So it's not like a normal physical wave that's just flowing through 3D space. It's a bit of an odd beast already. On the other hand, a different point of view, the long history, says that the quantum state should be thought of as epistemic. So the quantum state under this view encodes an experimenter's knowledge or information about some aspect of reality. There are various arguments for that point of view, arguments for why we should think of psi being epistemic. And one of the most obvious of those is just the fact of the collapse of the quantum state. When I do measurement, the state collapses, and I have described the system using a collapse state after the measurement. And of course, if I start with an entangled pair of particles and measure one end, this even happens at a distance. And the argument goes that this collapse is just like Bayesian updating of probability distribution. So we should think of it as being a similar thing in the quantum case. So here's Bill Unruh expressing that view. Wave function, not a thing that lives in the world, tool used by the theory to make inferences. Once one knows more, the wave function changes, so it is only there to reflect within the theory knowledge one assumes one has about the world. Here are some other sort of similar arguments for quantum state being epistemic. First of all, we know that non-orthogonal quantum states cannot be reliably distinguished, and that's just like classical probability distributions. Quantum states are exponential in the number of systems, meaning that if you count the number of real parameters that you need to specify the joint quantum state of n systems, well, that number is exponential in the number of systems. The same is true of probability distributions. You think of the probability distribution over, let's say, n classical bits. Number of real parameters to specify that distribution that's exponential. And many other things. Quantum states cannot be cloned, can be teleported, and so on. And in these senses also they're behaving like probability distributions. Okay, so what this no-go theorem that I'm going to show you, roughly speaking, is intended to show is that if we assume that there's some objective physical state of the system underlying the quantum description, something corresponding to the xp of the classical particle, and if psi merely represents information about that, then actually we obtain predictions that are different from quantum theory. Okay, so I want to introduce some of these arguments quite slowly. And to do that, it helps to consider just first of all a discrete quantum state space, or the state space of a discrete classical system. So let's think about a six-sided die. So, suppose the die is rolled, but I don't look yet at what the outcome is. There is some outcome. That we will take to be the ontic state of this die. So lambda, this refers to whichever of the six faces is uppermost. But not having looked at it yet, I don't know which face is uppermost, so I might assign a probability to each of the possibilities. So I'll have an epistemic state, which is a distribution rho. let's consider the following device. It's a sort of device for rolling the die. It has two buttons on it, one marked P and one marked E. And the way it works is it manages to roll the die in a biased way. So if I press the P button, this device rolls the die and the die comes out, but it's not a fair roll. Actually, if I press the P button, the device manages to strew things such that the outcome is always prime. So you always get 2, 3 or 5, and never one of the others. So if I press the P button, the probabilities I'm assigning to the outcomes are like this. If I press the E button, the device behaves differently and manages to roll the die in such a way that the outcome is always even. So in that case I assign these probabilities. Third each for 2, 4 and 6. And now let's think about this question. First of all, I'm going to use this preparation device for the die, pressing either the P or the E button. And then the die is fed into another device, a sort of measurement device which looks at it. And the measurement device has a pointer that can go to P or E. And what we want to happen is that the measurement device will indicate which button was pressed on the preparation device here. And I'm asking, is this measurement possible? And the answer is no. The measurement device cannot tell with certainty whether the P button or the E button was pressed, because all it has to work with is the die itself, which goes into it. And of course the outcome, lambda equals 2, can happen with either the P or the E preparation. So when lambda equals 2 happens, the measurement device doesn't know which way to go. And this is really just amounts to the simple observation that we cannot reliably distinguish overlapping probability distributions. Here's a slightly more involved scenario. We're going to ask again, is this measurement possible? Two devices now being used independently. Each one is the same as before. It has the P and the E button. So we get two dice rolled. One has state lambda 1 and the other state lambda 2. Both dice are fed into the measuring device. But this time it has 4 outcomes labelled not EE, not EP, not PE, not PP. And the way we want it to behave is that it indicates one of these 4 outcomes. And with certainty, if this measurement device is working, you can conclude that that particular combination of buttons was not pressed. So for example, if I press P and P, the pointer can go where it likes, as long as it doesn't go to the not PP outcome. And we'll ask, is this measurement possible? And the answer straight away is no again, because it doesn't matter which buttons I press. There is some chance that I have a 2 on this die and a 2 on that die. And in that case, it could have been any of the 4 combinations of button presses, and there's some chance that the pointer goes to an incorrect outcome. Okay, so now we're going to move to quantum systems and think about a similar sort of setup. So I've got a preparation device that prepares a spin-half system. I can press either a Z or an X button. And if I press the Z button, it prepares spin up Z. If I press the X button, it prepares spin up X. So again, we can ask, is this measurement possible? This would be the one where the pointer simply goes to Z or X and tells us which preparation it was. The answer, of course, is no, because you can't reliably distinguish non-orthogonal quantum states. So let's ask the question, well, why is that? Why can't we reliably distinguish non-orthogonal quantum states? Well, from the point of view of someone who believes in ontic models, that is, in some kind of underlying physical state of this system, a very natural explanation of this fact would be that actually these 2 different preparations, Z and X, some of the time prepare the same underlying ontic state of the system. When that happens, the measurement device doesn't know whether the Z or the X button is pressed. However, now when we move to this situation with 2 devices, we find a difference from the classical case of the die. pairs spin up z or x, this pairs spin up z or x. And the idea is that this measurement device has 4 outcomes. But for example, if z and z were pressed, it should never give you the outcome not z, z, and so on. And I'm claiming that this measurement actually exists. And it's quite easy to see. It's a measurement, it's an entangled measurement on the 2 spin half particles, and it projects onto this basis here of entangled states. So all you need to do is check the following. For example, if you look at this state here, well, its overlap with the up z state is 0. So if you prepared up z, you will never get that outcome. So that's the not z, z outcome. If you prepared up z, up x, you will never get outcome number 2. If you prepared up x, up z, you will never get outcome 3. And if you prepared up x, you will never get outcome 4. Okay, so that's how you build a measurement device. So what have we learned from this? What we've learned is that it cannot be the case that preparation of spin up z and spin up x can sometimes result in the same underlying quantic state. Otherwise, the measurement would be impossible for the same reasons that it was impossible when we're done. So the theorem I'm actually going to show you is along similar lines, but what we do is that we show that a similar argument goes through for any pair of distinct quantum states. So, now we'll start to do things a little bit more formally. Recall first of all we defined ontic models in the last lecture. So, consider a quantum system of dimension d. An ontic model defines the following things. Some space of ontic states lambda. For each preparation p of the system, a probability distribution mu p over lambda. For each measurement m with outcome k, a response function psi subscript m and k over lambda, where this is understood as the probability of getting outcome k when measurement m is performed, and the ontic state is lambda. So there's the basic setup, and of course we want the ontic model to recover quantum predictions. That means this integral should be equal to the predicted quantum probability given by the Born rule. Now, suppose that we have some ontic model. And suppose that in that model, for every pair of distinct quantum states phi naught and phi 1, the distributions mu naught and mu 1 do not overlap. So they have disjoint supports. Well, in that case, the quantum state can be inferred from the ontic state. If the ontic state is in here, then you know for sure that the quantum state prepared is phi naught, and you know for sure that it wasn't phi 1. So in that case, it's reasonable to say that the quantum state is a physical property of the system, and you can't coherently maintain the view that the quantum state represents mere information about the underlying quantum state. That's the idea. So, if a ontic model has that property, we'll say that it is psi-ontic. The other case, of course, is where for at least some pair of states, corresponding distributions mu naught and mu 1 can overlap. So here's an example of that. In that case, even if there just exists one pair of states for which there is this overlap, we'll say that the model is psi epistemic ontic model. And in that case, given an ontic state lambda, which is from the overlap region, such as lambda above there, knowing only lambda, you cannot infer whether the quantum state phi naught or phi 1 was paired. So these definitions, these distinctions, I should say, were originally introduced in this paper here. Okay. And the no-go theorem is going to say that psi-epistemic quantum models cannot recover predictions of quantum theory. So, suppose, for the purposes of getting the contradiction, that there are distinct quantum states, phi naught and phi 1, corresponding to distributions over ontic states mu naught and mu 1, and suppose that there's some subset S of the ontic states, such that for every lambda in the subset S, we have that mu naught of lambda is greater than 0 and mu 1 of lambda is greater than 0. So they overlap in this region. And suppose that the probability of getting a lambda from that region under the distribution mu naught is at least q, where q is greater than naught. And similarly, mu 1. Now, for the theorem, we need to assume one more non-trivial thing, which is this. I'll call it preparation independence. So, suppose we have independent preparations of quantum states that I'll just call phi A and phi B, which therefore produce a joint state that's just a direct product, phi A tends to phi B. So here's the A preparation, distribution mu A over lambdas. Let's call the ontic state of this guy lambda A. Here's the B preparation, distribution mu B, ontic state lambda B. Well, the assumption of preparation independence says, I suppose, I mean this isn't written, but first of all it says that the ontic state pertaining to this joint system is in fact just the pair lambda A with lambda B. But more than that, it also says that when you do this preparation of the product state, the joint distribution over lambda A and lambda B is just the product of the individual distributions. So, it seems to me this is a pretty weak assumption. I mean, in many ways it's a sort of standard assumption in experimental science that you can do independent experiments or independent trials of things, and when you do that, variables in those trials are independent of one another. And this assumption really just has that sort of character. These preparations don't need to be next to each other. We could have one on Earth and one on Mars being operated by a completely different team who don't even know about the other lot. So it's an implausible kind of conspiracy theory. One could argue that would violate this assumption. Okay, here's the actual argument. We're going to have to consider n systems rather than just two. So suppose that we prepare n systems independently, and then in a minute I'll tell you how large n needs to be. Each system we prepare in either the state phi naught or phi 1, where this is any pair of distinct quantum states. So here are n different preparations for each one. Here you can think of the device as having a lever on it if you want to, which you can move left or right to prepare either phi naught or phi 1. And there are therefore 2 to the n possible joint states that we might be preparing. Phi x1 to phi x2 to phi xn. where each xi is either 0 or 1. And when we do these preparations, the ontic model will predict some ontic state associated with each of the n systems. Now, here's the point. Given that assumption of preparation independence that we had, and also given the assumption that phi naught and phi 1 correspond to overlapping distributions mu naught and mu 1, and are non-zero all over some region S, then whichever of those 2 to the n product preparations we do, there is some chance that for every one of those n systems, the ontic state that you get coming out is actually from that overlap region. And the probability of that happening is at least q to the n. And now here's the problem, that this is where we get a contradiction from. For large enough n, there exists an entangled measurement across these n systems which has 2 to the n outcomes, and they correspond to projectors p1 up to p2 to the n. And the measurement is what was called a PP measurement by Case, Fuchs and Schack, who studied these things. It has the following property with respect to that particular set of states that we're preparing. The outcome P1 has 0 probability on the state, that's all phi zeros. The outcome P2 has 0 probability on the next one, the preparation where they're all phi zeros except this guy, which is a phi 1, and so on. And the projector P2 to the n has 0 probability if the preparation was all phi 1s. So for each of the 2 to the n states, one of these projectors has 0 probability according to quantum theory. And for each of these projectors, there's one of the 2 to the n preparations that gives it 0 probability. However, as we've just been arguing, for any of these 2 to the n joint preparations, there is some non-zero probability that the ontic state coming out, that's the n tuple lambda 1 to lambda n, is from, well, it has the property that each lambda I is from the overlap region of the mu naught and mu 1 associated with the single system. And that means, roughly speaking, that the measurement device, when that happens, has no idea which of the 2 to the n preparations it was. Could have been any of them. Any of them is consistent with the ontic state that has come into the measurement device. So the measurement device can't give outcome P1 because there is some chance that the preparation actually was all phi naughts, and yet quantum theory says if the preparation is all phi naughts, you should never give P1. And it can't give the outcome P2, and so on and so on. So this is the probability of getting outcome I. We just argued it should be 0 for any I. But of course it has to give some outcome, because those probabilities have to sum to 1. So there's the contradiction. And that establishes the no-go theorem. So given only preparation independence, and the assumption that for some pair of states, phi naught and phi 1, distributions mu naught and mu 1 overlap, we've obtained a contradiction with the predictions of quantum theory. So here's a little more detail about that measurement that you have to do. The last slide I just claimed that it existed, but here's at least one way of actually implementing that measurement. Previously I just said choose n large enough. Well, large enough means this. two states which are distinct without loss of generality, we can write them in this way, just by choosing our 0-1 basis appropriately. They don't have to be qubit states necessarily, by the way. Whatever dimension the system has, these two states will span a subspace of 2 dimensions. So we can choose a basis in that subspace this way, and write them like this. Okay. Now choose n large enough such that this holds. And then here is a circuit that implements the necessary measurement. You do a sort of a phase gate parameterized by beta on each of the systems. And you do this alpha gate, which just puts a phase parameterized by alpha on the all zeros state. And leaves all other basis states alone. And these are just Hadamard operations. And then you just do a computational basis measurement on the system. Okay, and it's a sort of one-page calculation to show that the circuit has the necessary properties. Now, we should think about noise a little bit. Bell's original theorem that he published appealed to the perfect anti-correlations that you get from a singlet. And it wasn't until a few years later CHSH gave a sort of noise-tolerant version of Bell's argument, so that you actually do experimental tests. With the Cauchy-Specker theorem, we've already seen that there's a bit of an issue to do with finite precision, in that you can find dense subsets of the unit vectors of Hilbert space which can be covered in the Cauchy-Specker manner. So the first thing we have to worry about here is the proof I've just given you, and that's a sort of fact about perfect precision that you wouldn't be able to test in a lab. And the answer is no, you can sort of do a suitable analysis of the noisy case and still get a result. Suppose that we do some real experiment in which we prepare those systems, do that measurement, and suppose that the measured probabilities that we actually get are within epsilon of the quantum predictions. Then what you can show is this inequality here. So this is the classical trace distance between mu0 and mu1. Actually, I'm going to define that on the slide that's coming up, but I realise I should have defined it here because I don't think this is the first time we need it. Anyway, the classical trace distance is a measure of the distance between two distributions, so it's 0 if they're identical, it's 1 if they're completely disjoint. And what we have here is a lower bound on that, which tends to 1 as the noise epsilon gets small. So as the noise gets smaller and smaller, this trace distance is tending to 1, and we're approaching the case where they are disjoint. So with a well-performed experiment, we can put an upper bound on how much these classical distributions can overlap. Okay. Now the theorem I just showed you did need to make use of multiple systems, and it did need that preparation independence assumption. Of course, with Bell's theorem, we've had several decades of debate about the sort of, the famous loopholes of Bell's theorem. So what if the settings are correlated with the variables, and what if there's backwards causality, and so forth. It would be nice to have some kind of theorem where we don't need that preparation independence assumption, if only to avoid those kinds of debates. Even though I've already argued that I take it to be reasonable. So let's see what we can say in the case where we're only analysing a single system, and we're thinking about ontic models for a single system and measurements on that system. without needing to think about multiple systems. So the first thing to say is that, well, epistemic ontic models for single systems do exist. So you can write down an explicit ontic model that covers correctly all the predictions for projected measurements on a d-dimensional system, and where the mu0 and the mu1 overlap for at least some pairs of states, phi0 and phi1. So an explicit construction like that is given in this paper here. However, that construction has the property that mu0 and mu1 only overlap for some pairs of quantum states. So Aronson et al. In this paper go a bit further. They provide an explicit construction such that those classical distributions overlap for any pair of non-orthogonal state vectors phi and psi. So that's also something that can be done. However, both of these constructions do have the property that the amount of overlap that there is between those classical distributions gets very small as the dimension increases. So what I'm going to finish off with is a theorem that says that something like that must be the case. So we're thinking about ontic models for single systems now. How much can these things overlap? So first of all, consider two preparations of a classical system corresponding to distributions mu1 and mu2 over lambda. So lambda is just some classical system now. Someone else is going to prepare this system and then give it to you, and you're going to try and guess which preparation they used. And your a priori probability for each of the possibilities is 1.5, let's say. And you're not going to repeat this over and over, you just have one go with the system that they give you. And with a single shot measurement on that system, your probability of guessing correctly, if you guess in the most intelligent way, is given by this. That's 1/2 into 1 plus d of mu1 and mu2. So that's the classical trace distance I was talking about. And there's the definition of it. Okay. Now suppose we play the same game with quantum systems. So someone else is going to prepare a quantum system in either of two states phi and psi, a priori probability of 1/2 each. I'm going to do a measurement, single shot measurement on the system and try to guess which preparation method was used. What if I use the optimal measurement for doing that? My probability of guessing correctly is 1/2 into 1 plus this, where that's the quantum trace distance between the states phi and psi, which is defined, at least for pure states, by that expression there. And here's an easy theorem. It says that in any ontic model that reproduces the predictions for a d-dimensional quantum system, for all pairs of states phi and psi, you must have this. So this is saying that the classical trace distance between the distributions mu phi and mu psi has to be at least quantum trace distance between phi and psi. And here's a sort of hand-waving sketch of proof of that. Think about the optimal quantum measurement that you're going to use guessing the preparation. Well, you will guess correctly with this probability. It depends on the quantum trace distance. But think what the ontic model says about what that measurement device is doing. It says that some lambda goes into the measurement device, which then produces an outcome. The measurement device only has access to lambda. And the measurement device is essentially distinguishing mu phi from mu psi. There's no way that the measurement device could achieve that success rate if mu phi and mu psi overlapped too much. In fact, there's no way it could do so if this trace distance was any smaller than that one. So that gives us this theorem. So that's some kind of constraint on ontic models. So let's make a definition. If we have an ontic model where this holds with equality, let's call that maximally psi-epistemic. Because in that case you have the maximum overlap possible between the mu's, consistently with the theorem on the last slide. And what we're going to ask is whether you can find models of that form. But first, why is this a natural definition anyway? Well, something that I said earlier was that I was talking about the fact that you can't distinguish quantum states phi and psi with certainty. And I said that a very natural explanation of that would be that there's some underlying ontic state and that the mu phi and the mu psi overlap. So at least some of the time you get a lambda from the overlap region, and that's why the measurement device can't always tell which the preparation was. Now, if we have an ontic model that's maximally psi-epistemic, like this, it gives a particularly good explanation for that fact. Because the failure to distinguish phi and psi in that case is entirely due to the ordinary classical difficulty that the measurement device has in distinguishing the probability distributions mu phi and mu psi. And that means that no other limitations or uniquely quantum effects of any kind need to be invoked to explain this difficulty of discriminating these two states. Okay, and here's the theorem that I want to show you. So a consequence of this theorem is that no maximally psi-epistemic model can recover the quantum predictions in dimensions of 3 or more. And the theorem says, in fact, slightly more than that. Now, to write it down, it's actually easier to talk about overlap of distributions rather than the distance between them. So let's define classical overlap just to be 1 minus the trace distance, and quantum overlap just to be 1 minus the quantum trace distance. Now consider an ontic model that reproduces quantum predictions in dimension d. And suppose that it satisfies this thing for all pairs of states phi and psi. So this says that the classical overlap is greater than or equal to alpha for some constant alpha times the quantum overlap. So if it were a maximally psi-epistemic model, then we would have equality here and alpha would be 1. What the theorem tells us is that alpha must be less than this, 4 over d minus 1, and actually if d is power prime, we write something slightly stronger, alpha is less than 2 over d. So not only is the overlap of the classical probability distributions smaller than the quantum overlap, but it gets smaller and smaller as d increases. So this result is sort of in the spirit of the no-go theorem that I showed you earlier. It's not as powerful, of course, because we haven't shown that the classical overlap is 0 between mu phi and mu psi. We haven't shown that that is joint. We've only shown that it's bounded by something. But we have managed to do that only by considering a single system. Okay, there is a noise-tolerant version of that result, which says that maximally psi-epistemic models cannot approximately recover quantum predictions in dimensions greater than or equal to 3. In d equals 2, we know that an explicit model does exist that is maximally psi-epistemic. So there's not going to be any theorem ruling that out. It was constructed a long time ago by Koshin and Specker. And actually quite recently, a similar thing was proved by Matt Leifer, who just got better, a much better bound. It has a dependence on the dimension that goes exponentially. Okay, so here's a summary of some of that. First of all, given preparation independence, psi-epistemic models cannot reproduce the predictions of quantum theory. Without preparation independence, you can still derive interesting results by considering single systems. for at least some pairs of quantum states, the overlap of classical distributions must be small as d gets large. A question that's pretty much still open is, are there information theoretic applications of these new theorems? Are there sort of tasks of some kind where quantum systems will get an advantage over classical systems as a consequence of these results? This isn't something that's really being explored yet. And that's pretty much the end of the 3 lectures. So let me just conclude with some final remarks. First of all the no-go theorems we have considered begin with a similar sort of idea, which is the idea of a classical or hidden variable or ontic model, whatever you want to call it, for a quantum system. And then they tell us slightly different things. Bell's theorem tells us that that model cannot be locally causal. The various extensions of Bell that we saw tell us that in various other scenarios the model cannot respect the underlying causal structure in other sorts of ways. Cauchy-Specker tells us that if it's a deterministic ontic model, it cannot be KS non-contextual. Beckens showed that the model cannot be preparation non-contextual. Today we saw that the model cannot be psi-epistemic, and those more recent results today show that even for single systems it cannot be maximally psi-epistemic. So largely I'm going to leave you to sort of take away from that what you will. But here are some sort of scattered thoughts. One approach, given all these theorems, is simply to accept all the conclusions of all those theorems. So for example, in the de Broglie theory, it is non-local, it is preparation contextual, it is psiontic, and all of the things that these theorems tell us it has to be. Many quantum scientists would take the view, on the other hand, that these theorems are evidence, not that we should accept the conclusions of the theorems, but rather that some of the assumptions need to be given up. Now you can fiddle with the sort of individual assumptions that each theorem has, but more importantly, the primary assumption that they all share is just this idea of an ontic model, that there's some underlying theory whose schematic form is well captured by that notion of an ontic model that we defined. So what I think I take from these theorems is that there remains the possibility that there's an underlying theory to be discovered, which simply is structured quite differently from the way in which those ontic models describe the world. Just returning now to something I started with at the very beginning, another way of thinking about these no-go theorems, rather as being results in foundations, is as constraints on classical simulation of quantum systems. Bell non-locality already has many applications in communication complexity, key distribution, measurement-based computation, and so on. It remains to be seen what applications might emerge from the generalized Bell scenarios that I talked about, or from preparation contextuality, or the PBR argument that we had today. But I expect these to be active research areas in the future. And finally, I have of course missed out a great deal of topics. So there's an awful lot that could have been said about all those theorems that we didn't do. Let me just finish off by saying one thing. One thing we really didn't cover is the connections that exist between those different theorems. So for example, given a proof of Cauchy-Specker contextuality, you can turn that into a proof of Bell non-locality. Given a proof of Bell non-locality, you can turn that into a proof of preparation contextuality. Given a proof of PBR type result, you can turn that into a proof of Bell non-locality, and so on. And in an even more thoroughgoing way, you can sort of see Bell non-locality as a special case of contextuality and describe the two in a much more unified way. So see Samson's lectures for more about how to do that. And that's it, I'll stop there. Thanks.
So it seems at the beginning of your proof that you started with the assumption that the distributions for two different wave functions have an overlap of positive measure.
Yeah.
But that's not the negation of they don't overlap. Could you deal with the possibility that they can overlap on a set measure 0? Possible loophole.
Yeah, so as pretty much throughout the lectures I was playing a little fast and loose with measure theory.
Not possible with measure 0, but that's
so they could overlap on a set of measure 0 and still reproduce quantum predictions.
Yeah.
That set of measure 0 is, when you write down your integral and say that you have to recover the quantum predictions, well, it's not contributing anything to the integral, so it doesn't really matter.
So then doesn't that mean that you can't actually rule out psi epistemic theories?
Sorry, say that again. What
I mean,
can we rule out?
Could you imagine a model where the distributions for different wave functions overlap so that the wave function is not a real thing, but it still reproduces?
I think the best thing to do would be to consider that case to be psiontic if they are only overlapping on sets of measure 0, if you want to do this properly.
I mean, sets of measure 0 can be huge, they can be infinite.
Yeah. But I'm not sure there's a sort of interesting loophole or anything like that here. I think it's just a question of arranging our definitions appropriately. So let me call that case as included in the definition of psiontic, and then I'll say I rule out epistemic models.
Yes. Here was about, I think, overlap about states or probability distributions, and I was wondering if this is somehow connected to this joint measurability, right? There's an overlap between measurements when I was considering.
What do you mean by joint measurability? You're talking about...
Don't know the exact definition, but I think A and B is jointly measurable if there exists another measurement which somewhat commutes with A and B individually, like the weak commutating measurement.
Well, if A and B are problems, for example, you could say that they're jointly measurable if there exists some other problem such that if you collect its outcomes together in a certain way, you get the positive operators in A, and if you group them in another way, you get the positive operators in B. So that's a sort of common definition, for instance, and then it's quite a difficult problem actually to determine which sets of those problems are jointly measurable. But anyway, so given some notion of joint measurability, what was the question?
Well, if this is related to these overlapping sets, where once joint measurability kind of considers the measurements, while it's understood this considers the state.
It's, yeah, I keep wondering if you can sort of turn the whole argument around and say things about measurements rather than states, so rather talking about overlapping news, say something about measurements. And, it's sort of very tempting to do that somehow, and yet every time I thought about it, it hasn't led to anything interesting that came out. Yeah, but it's a good thought.
Okay.
So just wanted to make a comment on what Nadish said first. So I have previously talked about how one can give an alternative dual definition of things being ontic or epistemic, which avoids this problem of having to deal with sets of measures. also wanted to ask a question. So, could I get you to go back to the slide where you introduced preparation independence? So, I just wanted to say what we were kind of discussing yesterday. So you've motivated preparation independence here as a kind of a physically reasonable assumption. But I would like to propose another physically motivated assumption and say that all I require for independence is that the ontic state at A is independent of the preparation made at B, and vice versa. Now this is subtly weaker, and I can show that under this slightly weaker assumption, your argument no longer holds. I'll talk about it at QPL in a couple of weeks.
Shane has interesting work on this, which is what he's just been talking about. And there's also interesting work by the group of Joe Emerson, who also had a paper sort of exploring a related idea. Well, actually, my apologies. I think I should have at least cited those two papers on the slide. I figured I didn't have time to really get into a discussion about it during the lecture. So Shane and also Emerson and others have thought about whether you can weaken this assumption in interesting ways, maybe such that the theorem doesn't go through, without it being crazy. During the lecture I was sort of arguing, I was trying to present a strong case whereby this preparation independence is something really that's quite fundamental to experimental science. Now, let me start with the idea that Emerson and others have. They consider that these two systems here, even though we're doing independent preparations, the ontic state of the joint system might not be captured simply by the pair lambda A and lambda B. They consider that the ontic state for the combined thing might have an extra component that you can think of as a sort of holistic component of the ontic state that pertains to both systems together somehow. But you won't ever notice if you only do local measurements on one or the other. So the overall ontic state is lambda A and lambda B and this extra thing. And then they introduce a sort of weaker notion of preparation independence, which is this. Given these independent preparations, you'll get some distribution over those three things. But the weaker notion of preparation independence is that if you marginalize over that third thing, the holistic one, and only look at the marginal distribution over lambda A and lambda B, then that thing factorizes. And they show that with this idea you can get around the theorem, because when these two systems go and have the entangled measurement done on them, well, the measurement device sees that extra holistic degree of freedom too, and its outcome can depend on that. And that enables you to get around the conclusion. Yeah, it's a good idea. Now what Shane was just describing was something of his own, which, you'll tell me if I get this right. It's slightly different. So we've still only got the lambda A and the lambda B. And we're dropping the idea that this mu has to factorize. But we are maintaining some notion of independence, which is this. In the actual arguments, remember we have this guy choosing between preparing phi naught or phi 1, and this guy choosing between preparing phi naught or phi 1. And so that the weaker notion of independence that Shane's talking about is that if you look at the, although the joint thing doesn't factorize, if you look at the marginal over lambda A over here, at least it doesn't depend on whether this guy is choosing the phi naught or the phi 1 preparation. So there's kind of a no signaling idea to it, and you were saying that way you could also get around the theorem, I take it.
Yes.
Yeah. Yeah, I mean, I don't quite know what to do with these ideas at this stage, I think, to be fair, but thanks, they're good ideas.
Any more questions?
Just very quickly, as a neophyte, when you went past this slide, I did wonder about that assumption. So I'm glad that it's,
Okay.
it does seem that there's always a bigger picture. So the idea of these things from independent seems a bit questionable. And your statement that it underlies experimental science didn't really reinforce the assumption.
You seemed a little bit too insistent, John, that it was a very natural assumption.
Some kind of preparation independence assumption underlies experimental science. In the case of Bell's theorem, there are a few people who take quite seriously the idea of superdeterminism where the settings are correlated with the given value. Famously toothed in recent years, but there aren't very many people who take that idea seriously. So So we have to maintain some notion of preparation independence. I think maybe the question I have is whether the weaker notions of preparation independence that Shane and those others come up with is sort of sufficient to ground experimental science. And let's put it something like that.
Could you say a little bit more about why it's justified to assume things in a pure product state, this preparation independence, rather than just that we just sort of effectively assume these systems are
Well, I've written the quantum state as a product state, just because that is what quantum theory would assign if these are independent preparations. What I'm appealing to here is not that I'm not saying quantum theory assigns a product state, therefore it must be that this thing factorizes. Because after all, there could be situations where quantum theory assigns a product state for two things that are close together and have been interacting modes. It's just that right now they happen to be in a product. So no, the argument is more just that we have that they genuinely are, by all our sort of usual reckonings, independent from one another, these two preparations, and that's why we expect this thing to factorize. And as it happens, yes, in that case, quantum theory will assign a product. Is this answering your question?
So it's a statement about how the theory is understood and applied, rather than something about something physical.
How which theory is applied? Quantum theory or
Quantum
the
theory.
quantum model?
It's sort of asserting quantum theory would give this product state.
Yes. Are you dubious about that? I feel comfortable saying that, I think. Well, okay. Now people can start to talk about sort of entangled vacuum states or sort of symmetric states of boson systems, and so we would have to have a deeper discussion. Sort of this level, I think it's a good stuff.
But presumably what Alex was just saying would have more of an effect if you were trying to do an experimental realization of this. You know, we're not, so I guess someone should mention Everett eventually. If you're an Everettian, then you presumably wouldn't think that on some logic level there is a product state, but it's actually just some part of some massive entangled state. So whilst the theorem will still go through, that's just not a situation you can come up with in a lab. It wasn't something.
I think I'd rather not stand here and try to think about what an Everettian should say about things. We could talk later. But, I mean, in a real experiment trying to test this thing, you do want to sort of get this independence as best you can. And so, for example, in the first experiment we had, these things were just sort of ions in a trap that were right next to each other. Sort of a fraction of a millimetre apart. So there, you know, one could really question whether you were doing independent preparations. And in a sort of more convincing experiment, you have the more separated.
We at Oxford and we were getting away without mentioning edit. So I think we should edit. I think we should edit this out.